Welcome back to Low-Level Programming Crashcasts. I'm Sheila, and as always, I'm here with Victor. Before we dive in, we'd love to hear from you. If you're enjoying our podcast, please take a moment to rate us on your favorite podcast platform. It really helps us reach more listeners who are passionate about low-level programming.
Absolutely, Sheila. Your feedback means the world to us. Now let's get into today's topic. We're wrapping up our chapter on number systems and data representation with a summary of everything we've covered.
That's right, Victor. But before we start, I have a quiz question for our listeners. Here it is. In a typical 32-bit floating point representation, how many bits are used for the exponent?
Ooh, that's a great question, Sheila. It really gets to the heart of how floating point numbers are represented in computers. Listeners, think about the components of a floating point number: sign, exponent, and mantissa. The distribution of bits among these components is crucial for balancing precision and range. Take a moment to ponder this. We'll reveal the answer at the end of the episode.
Excellent breakdown, Victor. Now, let's start our summary. We've covered a lot in this chapter, from basic number systems to complex data representations. Could you give us a quick overview of the number systems we discussed?
Certainly. We explored three main number systems: binary, decimal, and hexadecimal. Binary is the foundation of all computing, using only zeros and ones. Decimal is our everyday base 10 system, and hexadecimal, or base 16, is often used as a more compact representation of binary data. Each system has its strengths in different contexts of computing.
That's a great summary. I remember we talked about how hexadecimal is particularly useful for representing memory addresses. Could you elaborate on why that is?
Absolutely. Hexadecimal is favored for memory addresses because it provides a good balance between human readability and compact representation. Each hexadecimal digit represents 4 binary digits, so it's much easier for humans to read and remember 0-1A3F than 0-0-0-1 7. This becomes crucial when debugging or working directly with memory in low-level programming.
That makes sense. We also discussed signed and unsigned numbers. Could you remind our listeners about the key difference between these?
Of course, the main difference lies in how the most significant bit is interpreted. In unsigned numbers, all bits represent the magnitude of the number. In signed numbers, typically using 2's complement representation, the leftmost bit indicates the sign, 0 for positive, 1 for negative. This allows for representation of both positive and negative numbers, but at the cost of reducing the range of positive numbers that can be represented.
Right. And that leads us to an interesting point about potential pitfalls. What's a common mistake programmers might make when working with signed and unsigned numbers?
One of the most common pitfalls is mixing signed and unsigned integers in comparisons or arithmetic operations. For example, if you compare a signed integer with a large positive value to an unsigned integer, the result might not be what you expect. The signed integer might be interpreted as a very large unsigned value due to how the bits are interpreted. Always be explicit about your integer types and be cautious when mixing them.
That's a great point, Victor. Now let's move on to something a bit more complex: floating point representation. This was quite a challenge to wrap my head around. Could you explain the basic concept using an analogy?
Sure, Sheila. Think of floating point representation like scientific notation in mathematics. In scientific notation, we write numbers as a mantissa, or significand, multiplied by a power of 10. For example, 6.022 x 10 and 23, Avogadro's number. In floating point representation, we do something similar, but we use binary. We have a sign bit, an exponent, like the power in scientific notation, and a mantissa. This allows us to represent a wide range of very large and very small numbers efficiently.
That's a helpful analogy, thanks. One thing that surprised me was learning about the challenges with floating point precision. Could you elaborate on that?
Absolutely. The limited number of bits in floating point representation means we can't represent all real numbers exactly. This leads to rounding errors, which can accumulate in calculations. A classic example is trying to represent 0.1 in binary floating point. It results in an infinitely repeating binary fraction, which must be truncated, leading to small inaccuracies. This is why financial calculations often use fixed point or decimal representations instead of floating point.
That's fascinating. It really highlights the importance of understanding these low-level details. Now, let's talk about character encoding. We covered ASCII and Unicode. How has character encoding evolved, and why was this evolution necessary?
Great question. ASCII, or American Standard Code for Information Interchange, was one of the first widely adopted character encodings. It uses 7 bits to represent 128 characters, including English letters, numbers, and some special characters. However, as computing became global, ASCII's limitations became apparent. It simply couldn't represent characters from many world languages. This led to the development of Unicode, which aims to encode all possible characters from all writing systems. Unicode can represent over 1 million different characters, making it suitable for truly global computing.
That's a huge leap forward. It's amazing how much impact these underlying representations have on our daily computing experiences. Before we wrap up, Victor, could you share a fun fact or interesting anecdote related to our topic?
Sure thing. Here's an interesting tidbit. The year 2038 problem, also known as the Y2038 bug, is related to how some systems represent time. Many systems use a 32-bit integer to store the number of seconds since January 1st, 1970. However, this 32-bit number will overflow in January 2038, potentially causing system failures. It's a reminder of how the choice of data representation can have long-term consequences.
Wow, that's both fascinating and a little concerning. It really drives home the importance of understanding these fundamental concepts. Now, let's reveal the answer to our quiz question. Victor, would you like to do the honors?
Certainly. The question was, in a typical 32-bit floating point representation, how many bits are used for the exponent? The answer is 8 bits. In the IEEE 754 standard for 32-bit floating point numbers, also known as single precision, 1 bit is used for the sign, 8 bits for the exponent, and the remaining 23 bits for the mantissa.
Thank you, Victor. To summarize our chapter on number systems and data representation, we've covered binary, decimal, and hexadecimal systems, signed and unsigned numbers, floating point representation, and character encoding. We've seen how these fundamental concepts underpin all of computing and how understanding them is crucial for effective low-level programming.
Absolutely, Sheila. Understanding these concepts allows programmers to make informed decisions about data types, understand potential precision issues, and even anticipate future challenges like the Y2038 problem.
That wraps up our chapter on number systems and data representation. We hope you found it informative and engaging. Remember, if you're enjoying our podcast, please visit crashcasts.com, join our Discord community, or support us on Patreon. Your engagement helps us create better content for you. Until next time, happy coding.